Hello everyone, today I'll show the solutions to problems 5 and 6 of the high school round of round 184 of Prairie Math League. So for problem number 5, we have a circular plot which is 12 feet in diameter or with 6 feet radius. And we have a gravel path that cuts through the center of, cuts through the circular plot with one edge on the center of the plot and with 3. And now we wish to find the remaining area, which is not which is not like part of the gravel path. So like this part and this part. So this area is somewhat easy to find because this is just half the circle and we know how to do that. But this is a bit trickier. To find an area of such a thing, we note that we can connect these 2 points with the center of the circle. And now the area of this part here is equal to the area of this entire sector minus the area of this triangle. And now this gives us a more concrete way to find this area. Now note that this radius is 6 and this width is 3. Now if we just look at this here, this is a 30, 60, 90 triangle. So this is 30 degrees, 60 degrees, 90, and this is 3 squared to 3. Wait. So we know that this is 30 degrees and this is also 30 degrees by symmetry. Now this entire angle has like measure 180 degrees. So this part has measure 120 degrees. And 120 degrees is 1/3 of 360. So this sector here is 1/3 the area of the entire triangle, or sorry, the entire circle. And now we wish to find the area of the triangle. Now this triangle, this right triangle here is similarly a 30, 60, 90. So this is 3 squared of 3. Similarly, this is 3 squared of 3. Therefore, this entire thing is 6 squared of 3, and this has height 3. So the area of this triangle is just base times height divided by 2, or this, which is equal to 9 squared of 3. Now, this is the area of the triangle. The area of the entire sector here, which is 1/3 of the area of the circle, is going to be 1/3 times pi times 6 squared, which is equal to 12 pi. And the area of this semicircle here is going to be 1/2 pi 6 squared. Here we're using 1/2 because this is half the circle. We get 18 pi and 12 pi. So now we have, if we add these two things together, we get this plus this, but we don't want this triangle here, so we have to subtract this thing here. And our answer becomes 18 pi plus 12 pi minus 9 squared to 3, which is equal to 30 pi minus 9 squared to 3, and this is option choice E. Alright, for problem number 6, we have a coin that is 8 centimeters in diameter. So if our coin looks like this, then this is 8 centimeters. And it's tossed into a 5x5 grid of squares, each with side length 10. So each of these is 10 centimeters. A coin is in a winning position if no part of it touches or crosses a grid line. Otherwise, it is in a losing position. So if it's like this or like this, these are like losing positions because the coin is touching a grid line. But if it's like here, then we have a winning position because it's clearly not touching any grid line. And now we wish to, given that the coin, the entire coin does not, like no part of the coin goes outside of the boundaries of our space. So if we're given that, we wish to find the probability that it is in a winning position. So what we want to do is we want to characterize the location, each possible location of the ball, and correspond that with whether it is like a winning or losing position. So, or sorry, a coin. So if we have a coin, then one way to characterize it is by its center, and we're going to do that here. This coin has center here, here, and here, and and given its center, we wish to figure out whether a coin is in a winning position or a losing position. And but before we do that, we also have to figure out whether the coin even fits this condition. So to do that, we sketch any coin that is just touching the outside. The center ends up being like somewhere here. And and then it's not hard to see that this is 4 and this is 4. So any coin that lands within this, whose center lands within this square, satisfies. This square being like the square which is like with like 4 centimeter margins from the outside square. Because if it's anywhere inside of this, then it's always going to be like no part of it is going to come out. Its radius is at most 4. Its radius is 4 centimeters, so it's not going to go outside of this square. But on the other hand, if it's outside of this, then it goes out like here. So now we have characterized basically the sample space of all possible coin tosses, and the total area of this is going to be so this is 4, this is 4. Now each of these is 10, so altogether it's 50. But this side length is 50 minus these two margins, which is 50 minus 2 times 4, or in other words, 42. So each of these, the side lengths of each of these side lengths has length 42, and this is going to be the total area we're going to work with. So now that we've characterized this, the like overall probability, we need to find the probability that it's like winning. And again, we use this argument based on the center of the circle. So now consider a single cell here. If the center happens to be like here, then it's clearly going to go out. But if it's somewhere closer to the center of this square, then it's going to be inside. So now we ask, like, how can it be a winning position? Well, imagine it's a square here. So basically, every part of the radius has to be 4 centimeters, at least 4 centimeters away from any of the borders of this square. So if the center of the circle is 4 centimeters away from here, in other words, if we draw another, like a similar margin that we had over here with 4 centimeter margins, then the area inside this smaller square is going to characterize like the area that corresponds to the center with a winning coin. Now notice that this is 10 centimeters, this is 4, and this is 4. So this actually has only side length of only 2, which is quite a small square. But we also need to take into account that it can be inside any square. So we have one square of side length 2 here, one here, and we repeat across all possible, all 25 cells. We have a total area of 42 squared, corresponding to this entire possible space. And among these, we have 25 possible grid cells that a winning coin could fit into, each with corresponding area 2 squared. If the coin center can land in any possible position within any of these possible areas, then our probability corresponds to this, which is a fraction of area that is corresponds to a winning position. And now this is equal to, if we do the entire calculation, this simplifies to 25 over 441, which is option choice D, and we're done. Thank you for watching.